Cool.
All right, Andrew, take it away.
Okay, last talk. You can either fall asleep or maybe I'll wake you up or whatever. So slight change of title because I'll broaden the focus of my talk a little bit to talk more generally about satellite dwarf galaxies of the Milky Way, M31, and the LMC as we see in our FIRE simulations of such systems. And we've already heard from Anna and Sam about the properties of our sample here. I'll just reiterate for the rest of my talk. I'll be combining the latte suite of individual Milky Way mass systems, of which we have 8 now, we actually now have 3 local group-like systems. So Shay just finished the 3rd one. So that gives us 6 total halos that are located in local group-like environments right here. And I'll try to highlight in my talk some of the similarities, but also some of the differences that we're finding in our simulations of local group-like environments compared to just individual Milky Way systems in a cosmological settings. Sam and Anna already told you, our baryonic particle mass resolution in these simulations is between 3,500 and 7,000 solar masses. And here's just postage stamp images of the central galaxies that form across this suite of simulations. And I'll try to highlight some of the work of our growing galaxy formation group at UC Davis. So Sam already showed you her results combined with the work she's doing with Sarah. And I'll try to highlight some of the work of graduate students Daniel Samuel and Isaiah Santisteban, and also a little bit of the work of undergraduate Sierra Chapman. So first I'd like to tell you about one of the interesting differences we're finding between our simulations of individual Milky Way-like systems and in local group-like systems. And so this is a recent paper we put out led by Sher, Garrison, Kimmel looking at star formation histories of our satellite galaxies, but we also wanted to understand how this related to the star formation histories of the main host galaxies that form in these simulations. So this is just the normalized star formation history as a function of cosmic time, and all the lines here show all of our simulated sample, and we show in different color our local group-like hosts and our individual more isolated Milky Way or M31 mass hosts, right? So you can see we see a range of formation histories of these host galaxies, but we find systematically earlier formation histories of those forming in local group-like environments. And this shows nicely that, for instance, if you look at when each of them reaches half of their terminal stellar mass, we're seeing offsets of 1.5 megayears of when they're forming. And Isaiah Santisteban, who's out in the audience, raise your hand, Isaiah, has been looking at this in somewhat more detail to look at this across a broader cosmic time interval. And here you can see here, the black line is all of our simulated hosts. Gray is the isolated Milky Way hosts, and the dash curve is our local group-like hosts. And you can see that this difference, this systematic difference in the formation history, persists all the way back to basically the highest redshifts we probe, redshift 6 or redshift 7. So this is something we're starting to dig into. I don't think we have a full explanation for this yet, how much it has to do with the local groups forming in just more dense cosmic environments that leads to earlier collapse. There may also be some effects from more metal pollution promoting more efficient gas cooling when you have a more local group system. But I think it's interesting that I think of the 6 local group hosts we have, I think 5 of them are the earliest forming hosts in our entire sample. So I think this may increasingly become an important thing to think about when we're trying to use cosmological simulations like this to understand local group observations. So that was all I'm going to say about the central galaxies. Now to look at the properties of the satellite dwarf galaxies forming around them. This is a compilation of our sample. We had 2 of the local group systems finished here, so we can add 1 more onto this. So this shows the number of satellite galaxies forming within 300 kiloparsecs of each host as a function of the dwarf galaxy stellar mass. We can see M31 up here. Here's the Milky Way down here. And the different color lines show the satellite mass functions from all our different hosts. You can see there's a significant amount of scatter from host to host. We find a lot of the systems scatter close to the Milky Way. We have maybe 1 or 2 that scatter up closer to M31, although M31 does seem to have more than many of our simulations. Maybe it's a slightly higher halo mass than the mass ranges we've chosen to zoom in on these simulations. But broadly speaking, we're not seeing any tension in the satellite stellar mass function, at least down to the classical dwarf regime, stellar mass of 10 to the 5, which we can resolve. So I'm happy to say that the missing satellites problem remains dead and well. But not everything is necessarily in great agreement. So this is also from Shay's paper. If we look at the internal velocity dispersions, or really trying to measure the internal densities of these dwarf galaxies. So this is the usual sort of too big to fail type plot. So circular velocity as a function of internal radius. individual points show individual observed dwarf galaxies around the Milky Way, and the lines show the results, the internal rotation curves from our simulations. So if you just compare to the Milky Way, things look pretty good, right? We see broad agreement. But if we compare to the satellites around M31, or more broadly look at the local field going out to about a megaparsec around the local group, again, we're seeing broad agreement. However, what we are lacking is the population of dense sort of dwarf ellipticals, a lot of these NGCs you see up here. And it's not just an environmental effect around M31, we're also seeing that we're not forming any of these dense dwarf ellipticals in the local region. So this is something that we're seeing, that we're forming too few dense dwarf galaxies. And I think many simulation groups are finding this. It's relatively easy now to form low surface brightness, ultra diffuse type systems. But the key challenge, I think, going forward is in the same model space to simultaneously form sufficiently dense systems like dwarf ellipticals. So I think it's just another reflection of the so-called diversity problem in dwarf galaxies that we're seeing here. So that was the mass function and the velocity, the internal velocity dispersions of these satellite galaxies. Recently we've pursued what I think is a more rigorous test, or at least a complementary test, which is looking at the spatial distribution of satellites in these simulations. So this is work that Jenna Samuel, graduate student, also at Davis, raise your hand, Jenna, has been leading. She had a poster on this, which hopefully all of you saw. If you happen to miss it, I'll highlight what I think are the most interesting bits. So let's think about, so first of all, I'll just preemptively say, we started looking at planes of satellites, but we realized halfway through that it was important to get a much better benchmark on just the radial distribution of the satellites. So that was the topic of Jenna's paper here. So before I show you the simulation results, let's see what this looks like for the local group, so satellites around the Milky Way and around M31. So here what I'm plotting is the cumulative number of satellites as a function of their distance from either the Milky Way or M31. So what's interesting about the local group is if you look just out to 150 kiloparsecs, at least again, here I'm just limiting it to classical dwarfs. If you look just out to 150 kiloparsecs, the Milky Way and M31 look basically the same. It's only when you extend and look at the populations out to 300 that we see that factor of 2 difference between M31 and the Milky Way. M31 just keeps growing, and the Milky Way is almost flat beyond 150 kpc. It's kind of curious. Okay, so this is what the observations look like. Now let's look how our simulations look. Again, I just want to emphasize one of the key ingredients in baryonic simulations like this is the significant difference in the population of surviving substructure, especially in the inner halo. So this was a plot from a paper we had a few years ago of Shays, where we simulated the same system on the left, dark matter only, and on the right, you're seeing a map of the dark matter in the simulation that also includes all the baryonic physics. And if you look all the way out to the Vero radius, it's about a factor of 2 reduction in the number of surviving subhalos. But if you look in the inner 20, 30, 50 kiloparsecs of these hosts, it's about of order of magnitude reduction in the amount of surviving substructure, just as a result of tidal interactions with the disk. That's it. So the question I think has come up is this too much satellite destruction? Are we not forming, or are we not holding on to enough satellites that should be surviving in the inner regions of these hosts? Okay, so let's compare our simulations to observations. So again, the cumulative number of satellites is a function of distance. Again, showing M31 here, and then the black solid is Milky Way. And now the light blue here is basically the average across all of our host sample. The orange curve shows our local group-like systems, and the magenta curve shows our isolated Milky Way-like hosts. So you can see maybe some offset in this diagram, but note that it's well within the 68% scatter. So I'll say this, our interpretation is this, we don't think this is a big difference between simulating local group and individual Milky Way-like systems. But you can also see what's promising is that basically the 1 and 2 sigma scatter is basically bracketing what we observe around the Milky Way and around M31. And I can show that more directly by just plotting the ratio of the number of satellites in the simulation relative to what's observed. So here's that ratio for the Milky Way, right? So you can see basically all distances where our median in 68% is basically bracketing what we observe around the Milky Way, down to about 50 kiloparsecs, which is the closest distance that we have surviving classical dwarf around the Milky Way. And then we can do the same exercise for M31. Right? Remember, M31 has about twice the total number of satellites as the Milky Way, so not surprisingly, our overall normalization is a little bit lower. But again, we're not seeing strong scale dependence that would hint that we're over-destroying satellites at small distances. In fact, if anything, it's actually a better agreement at 100 kpc than it is out at 300 kpc. So we're seeing broad agreement in the radial distributions of these simulations compared to local group observations, which I think is an important benchmark of these sorts of simulations. So coming back to this interesting difference between Milky Way and M31, I think it's striking how concentrated the distribution of satellites is around the Milky Way. And the question is that common? Do we see these sorts of concentrated distributions emerging from these simulations, or is that actually rare? So let's just do the following exercise. For the same type of diagram I've been showing you before, cumulative number of satellites is a function of distance. And let's just select out those hosts. And also we're sampling back in time about 1.5 gig years, so we can get some sense of how much time-to-time variation there is in these hosts. And let's just select out between our 14 hosts and about 14 snapshots per host. We have about 150 samples. Let's just select out those snapshots that by selection have exactly the same number of satellites out to 150 kiloparsecs as the Milky Way does. And let's just ask, what does the resultant distribution of satellites from 150 to 300 kiloparsecs look like across our full suite of simulations? And that's shown here. So here's the median, 68, 95% of the distribution. So we almost never find any hosts, essentially, that are as concentrated as the Milky Way. So either the Milky Way is very unusually concentrated, right? It's basically a few percent outlier compared to the cosmic population. That's one possibility. Or there are more satellites lurking out here, even classical mass satellites around the Milky Way, that would help prop this up to be more cosmically representative, at least compared to our simulations. A few years ago, I might have been more reluctant to say this, but in the last 2 years now, we've discovered 2 new classical dwarfs around the Milky Way, Crater 2 and Antlia 2, that are just very low surface brightness, very extended systems. So our interpretation is that it's plausible that there are at least a few more lurking out there, especially at larger distances where they're potentially harder to find. And if so, that would bring up the Milky Way to be more consistent with our simulations. Or again, the other possibility is that the Milky Way is just very unusually concentrated in its satellite distribution. I want to emphasize that some of you may be asking, well, what about the LMC? Because we know that the LMC fell in, it's near pericenter. It's brought in the SMC with it. Is that part to do with here? And yes, I suspect it has part to do, but note that many of the Milky Way and local group-like simulations we have here do have LMC-like flybys. And in fact, that's been the work of my undergraduate student, Sierra Chapman, who, by the way, will be applying to grad schools this fall, and has been asking the question of, when we select out the 5 or 6 simulations that we have that at low redshifts have an LMC-like flyby, so an LMC mass halo comes within 50 kiloparsecs of our centrals, does that cause any modulation in the number of satellites in the inner regions of these simulations? So what we're plotting here is the ratio, essentially, of the number, really it's the infall rate of low mass subhalos in our systems that have LMC-like satellites near pericenter relative to our full sample, right? So is the Milky Way with the LMC representative, or is there some enhancement? And the answer is we do see significant enhancement on average. There's significant scatter. You can see here, this is just selecting subhalos of different masses, because we're also interested in how this might affect the population of ultrafaints around the Milky Way. And you can see it doesn't really matter as a function of the mass of the subhalos you select. Whenever we have LMC-like flybys, we have on average about a 50% boost in the number of faint low mass subhalos that could host faint galaxies in the inner 50 kiloparsecs, of these simulated hosts. Okay, so normally this is a section on star formation history, so I'll say a little bit about the star formation histories of the satellites in these simulations as well. So this is a paper that was led by Shea, Garrison, Kimmel that we just put out more recently. So taking the archaeological star formation histories of the dwarf galaxies and comparing them to what we can infer based on resolved stellar population measurements of dwarf galaxies in the local group. So this is, again, normalized star formation history, so from 0 to 1 is a function of cosmic time. So first I'll show our more massive satellites we resolved across our full suite. So this shows, the blue curve here shows satellites of our local group-like simulations, and the orange curve shows satellites of our individual isolated Milky Way-like hosts. And then the black curve here, the thick black line, is basically the average star formation history combining the observed galaxies in the local group. So in here, I think this would include, I think this is just the Milky Way, so it would include the LMC and the SMC. So you can see for massive satellites have star formation histories that basically continue down to redshift 0, so we don't see quenching environmental quenching happening at this mass scale, which is broadly consistent with, for instance, the LMC and the SMC around the Milky Way, which are still gas-rich and star-forming. But as we go down the mass function, so now these are satellites of stellar mass 10 to the 7, 10 to the 8, consistent with observations, now we start to see star formation histories that are truncated. It's kind of hard to see here, but these are actually truncated over the last 1 to 2 gigayears, consistent with the truncated star formation histories, i.e. quenching, of the sort of, think Fornax or Leo 1 around the Milky Way. And as we keep going down the mass function, we're also recovering the observed trend that our lower mass satellites systematically form earlier, they quench earlier as a result of both environmental effects of falling into the Milky Way or M31, and also effects of cosmic ionization at these earlier redshifts. And you can kind of see here there's some offsets potentially between the Milky Way and the local group, but they're well within the scatter. So our interpretation is for at least the satellite population, we're not seeing any interesting differences in the star formation histories between our local group-like simulations versus our isolated Milky Way M31-like simulations. So no differences in the star formation histories of the satellites. However, we are seeing interesting differences in the star formation histories of the near field, like local field central galaxies that are within 300 kiloparsecs and a megaparsec of these simulations. So let me show you that more clearly. So this is just looking at our isolated Milky Way-like hosts. Again, star formation histories as a function of stellar mass, 10 to the 8, 10 to the 9, 10 to the 7, 10 to the 8, 10 to the 6, 10 to the 7. Right? And so here are, the orange curve again shows the star formation histories of things that end up as satellites within 300 kiloparsecs. And then the magenta curve shows star formation histories of things that end up between 300 kiloparsecs and a megaparsec in our zoom-in region. So there's not big differences at the massive end, but as we go down to lower mass satellites, we're starting to see clear effects of environmental quenching, which is, I think, broadly consistent with the trends you see as you look around the Milky Way and M31 of the transition from dwarf spheroidals that are inside the halo of Milky Way and M31 to gas-rich dwarf irregulars that are in the near field. So based on just our isolated Milky Way-like simulations, I would say qualitatively we're seeing environmental effects that are consistent with the local group. However, if we do the same exercise in our local group-like hosts, we basically see no significant systematic differences between the star formation histories of the satellites and the near-field centrals. So what seems to be happening here is that even dwarf galaxies out to distances of about a megaparsec are being influenced by forming in these local group-like regions. So again, we're trying to dig into this. I don't have a clear-cut answer for you now. It may be some combination of virial shocks from these hosts extending to larger distances and driving stronger pressure in the IgM. It may also have to do with the collapse times of these low-mass halos that may also be forming earlier and therefore using up their gas earlier. We're trying to flesh this out, but this is one of the other interesting differences we're seeing between local group and isolated host simulations. All right, in my last few minutes, I just want to highlight some work we just put out a few weeks ago, not just trying to understand satellites of the Milky Way more generally, but also thinking about the possible connection of the satellite population of the LMC itself and the population of even ultra-faint dwarf galaxies that the LMC might have brought in with it. So this is in collaboration with Laura Salas and her student Ethan John at UC Riverside. So we also have a suite. So these are not Milky Way-like systems anymore. We have just individual LMC mass hosts. But what's nice about our suite of LMC mass hosts is we can push on resolution even more, some of which we've simulated at just about 900 solar mass resolution, so good enough to start to be able to model the satellite population of ultra-faints that are forming around these individual LMC hosts. So this just shows you, for one example, a map of the dark matter distribution of the halo. Here is basically pointing out where all the luminous satellites are around this host. And then we have a sample of 5 LMC mass hosts we'll look at here. So one question you might ask, I argued earlier that one of the big effects in agreeing with observations of the Milky Way is the tidal destruction effect from the disk of the Milky Way. So you might ask, well, do LMC mass hosts also exhibit a strong tidal influence on their satellite populations as well? So we can look at the population of subhalos. This is regardless of whether they're luminous or not. So just plotting subhalos as a function of their internal Vmax. For our 5 simulated LMC hosts, for the subhalos that are within 0.2 of R200. And then on the bottom panel, which is probably the one you should look at, is the ratio of the number of subhalos in a dark matter-only version of that host relative to the fully hydro version of that host. So here, just to calibrate yourself, is that ratio within 0.2 of R200 for our Milky Way mass hosts. So you can see ratios of 3 or 4 or 5, which is saying that there are 3 or 4 or 5 times as much substructure in DMO simulations as in baryonic for our Milky Way hosts. And this is the same ratio for our LMC mass hosts. You can see there's a slight enhancement, maybe 30, 40%, but it's very small. And I think this is exactly as you'd expect, simply from the fact that the stellar mass to halo mass relation of LMC mass hosts is factors of almost 10 lower than they are in our Milky Way mass hosts. And so just the mass perturbation from the central galaxies is so much weaker in the LMC mass hosts than in the Milky Way. So it doesn't really seem to matter of doing, as far as just the survivability of subhalos, whether you run these baryonic simulations versus dark matter only. And so here's the main plot from this paper. So again, the cumulative number of satellites above a given stellar mass. Now we're able to look at populations. Ooh, missed my chocolate. Just finish up now, down to below classical mass regime, so down to ultra-faint masses of something like 10 to the 4. We overplot on here the population of dwarf spheroidals around the Milky Way that are plausibly associated with the LMC. So there's actually some evidence now from updated proper motions of both Carina and Fornax that they may have been brought in with the LMC. I think this is still debated, but it's interesting to at least overplot across our simulated host sample here that we're finding some of our hosts that have massive LMC-like satellites, but of course some for whom their most massive satellite is more like between Fornax and Carina at 10 to the 7. We do find for those that do tend to have SMC-like satellites, they also tend to have Carina and Fornax-like satellites. There's not the sort of big mass gap you would get if the only satellites of the LMC were SMC and then you jump down to Hydra 1, which is potentially interesting. The other interesting thing is that almost all of our predicted mass functions seem to be much steeper at the faint end than plausibly linked with the LMC, which our interpretation is probably there's just more incompleteness of the ultra-faint population around the LMC. In other words, more ultra-faints yet to be discovered, if our simulations are correct. So I'll end there and just post highlights of what I think are the most interesting trends. So we're recovering radial profiles, I think, that are broadly agreeing with the Milky Way. Important differences in the formation histories of the hosts in local group compared to isolated Milky Way simulations. We're starting to be able to predict ultra-faint populations of satellite galaxies, and we are seeing systematic differences in the star formation histories of dwarf galaxies in the near field in local group-like environments versus individual Milky Way-like environments. Thanks.
Thank you very much, Andrew. Do we have questions? Okay, we'll start with Fanj.
Thank you, Andrew, for an interesting talk. So I want to have you look at the relationship between the radial distribution of satellites and the assembly history of the host. Because you know, like the concentration of the smooth dark matter distribution is a strong function of the formation of the halo. So maybe these are correlated. And since in your simulations you only have 6 systems, it may well be that your like assembly history.
14 systems.
Oh, 14, okay.
Yeah.
So, but still, it's a rather small sample. Maybe the assembly histories are not like fully sampled.
We haven't done that. I agree it's an interesting exercise to do. Although it's challenging to then translate that into a statement in comparing against the Milky Way or M31 because we also don't know what the assembly history of the halos of the Milky Way or M31 were. Yeah, sure. But I agree that would be, we haven't really done that and it would be worthwhile.
And also, have you checked how well the satellite distribution follow the smooth dark matter halo distribution?
No, we didn't. Okay. We didn't do that yet. But that'd also be worthwhile.
Okay, let's have one more question before we go into our discussion. Let's see.
I was wondering whether you looked at the distribution of the info redshifts for the satellite galaxies, and related to that, how, for the total amount of stars that you still have in the surviving satellites at redshift 0, how much mass has come in satellites that have been disrupted? Have you looked at the ratio in the stellar halo?
Yeah, no, sorry, yes. So we've looked at the stellar halos in a different paper that was just an independent analysis of the stellar halos that Robin Sanderson led that, but we haven't done the joint analysis of sort of combining the population of stellar halo with satellites. That would also be interesting. And as far as looking at infall times, that's also something that Jenna is planning to follow up on to see when these things fall in and how that might relate to their star formation histories or spatial distributions. But that's to do.
All right, let's thank Andrew again.